So, we talked about time dilation, length contraction, some physical way of looking at Doppler shift. But this is all like very physics based and intuitive, but there is a mathematical way of doing all this, and that's the that's the language of four vectors and tensor analysis and all that interesting mathematical stuff about relativity. So we will actually not be doing the tensor analysis and the formal relativity as much. Okay, we will mostly be using results. So so I will actually just mention a few things. Let's see. So this concept of four vectors, right? So it's useful to remember this concept of vectors in 3 space and then generalize it to what is meant by a 4 vector. 4 vector is a quantity defined in 4-dimensional space-time, in the 4-dimensional space of time and space, and actually this is how you call it. So just like how vectors and tensors are there in 3D space, this is a generalization of those concepts, which is valid when speeds start approaching the speed of light. Okay, so we know that we define this quantity called this s square equals minus c squared tau squared is equal to minus c squared t squared plus x squared plus y squared plus z squared, right? So this tau is called the proper time, right? So this tau is always less than or d tau is always less than or equal to dt, and in fact d tau equals dt by gamma, right? So so this is proper time. This is the shortest, right? So the time measured in the rest frame is the shortest, and in other frames the time scale which you measure becomes longer and longer. So this quantity is called an interval. S is called an interval, right? And this is a generalization of this measure of distance, right? In 3D space, you define distance as delta x1 squared plus delta y1 squared, delta x2 squared plus delta x3 squared. So this is a generalization in space-time. So in 3D space, right, when you do rotations and reflections and translations, the distance between 2 points is an invariant. Here, this interval is an invariant. This is a Lorentz invariant. Okay, and our Lorentz transformations are constructed such that this is equal to minus c squared t prime squared plus x prime squared plus y prime squared plus z prime squared. Okay. Okay, so right, so sometimes we talk about contravariant components of a vector. So for example, for x, and we sort of denote it with a raised Greek index x mu. So this can actually be thought of as x0, x1, x2, x3. Right, so these are coordinates. This is the time coordinate. So this is equal to ct. X0 is ct, x1 is x, this is y, and this is z. Right. So this is contravariant. When this index appears on the top, this is sort of like a component of a 4 vector. Okay, so this is called the contravariant component when this index appears on top. And similarly, we can actually so this ds square, we can actually write it as eta right, so eta mu nu dx mu dx nu, right? So again, I'm actually not doing a very formal thing. So here I'm assuming Einstein summation convention, that is the repeated index like mu and nu is summed over. Okay, so and what is eta? So eta can be thought of in a matrix form as well. So this is the Minkowski matrix, -1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So this is called Minkowski matrix, and what it does is eta mu nu, and this is also equal to eta mu nu. So both the contravariant and covariant Minkowski matrices are the same, and it's a symmetric matrix. So we can actually write this S squared as eta. We can write this as eta mu nu x mu x nu, right? So here you will, if you think about this as a matrix, you can actually construct it, right? So so this is the matrix, and you multiply this by a column vector, so you get a column vector, and then you so let's see, so if you have a 4 matrix, if you do eta mu nu x mu, so eta mu nu x mu is equal to, so this will give you x nu, right? So this is also called lowering of the index, right? So a contravariant component can be written, can be converted into a covariant component. These are just useful ways of writing the same matrix. So for example, let's see. So if you look at this, then this becomes minus ct x y z, right? If you just multiply this by eta, this matrix, you get minus ct, and if you do after that, x mu times x nu, this is a contraction, right? There are these index conventions where you're just summing over.
Sir, shouldn't the second one be a, row matrix, not a column matrix?
That's correct. So I'm actually just writing it as this, but yeah, the right, that's correct. So right, so this is correct. So you have minus ct x y z, and this is ct x y z, and if you just compress it, so basically you can actually write row or column, whatever you like, but the point is you can only contract the indices when they are, when you're dotting. So this is like a dot product of 4 vectors, right? So this is that, so which is nothing but s squared, which is a scalar. So this is a scalar. Right, so we can actually write this as x eta, something like this, right? This is a column vector, this is a row vector, and this is a matrix. So you get a number. That's correct. So this can actually be thought of this way. But as I said, I will really not do very much all these, but I will only sort of introduce the concepts, the one that we'll be needing. Similarly, so this is Minkowski matrix. Similarly, we can actually show, Lorentz boost, for example. So Lorentz transformations that we sort of studied, we can also look at it in a matrix form. So for example, x prime is equal to lambda x. So this is alpha, this is beta, this is alpha beta. So this is the matrix representation of Lorentz boost in the x direction. So lambda beta alpha is equal to gamma beta minus, sorry, just a second. This is gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 and of course 0 0 0 1. Right, so this is nothing but matrix form of writing Lorentz transformation. X prime, right, so x prime equals lambda x, right? So this is the boost along the x direction, but in general you have this Lorentz transformation matrix. Basically, this is a matrix which satisfies the preservation of this S square, right? All the this is just a special transform which corresponds to Lorentz boost in the x direction, but you can consider it in an arbitrary direction. You can also consider translation, rotation, all those that preserve this interval will be good transformation, good transformations which satisfy which satisfy this postulates of special relativity. Okay. Right, so let's see. So S square is equal to eta mu nu x mu x nu. This is also equal to eta sigma tau x prime tau x prime sigma x prime tau. Right, I'm just writing S square in the unprimed and the primed coordinates because this is independent of the frame from which you're looking at. So what does this give? This gives us this is equal to eta sigma tau lambda sigma nu x nu. I'm just writing this by using this definition of transformation of a vector x, and this is lambda tau mu x mu. So what do we have? We have this is equal to eta sigma tau lambda nu sigma lambda mu tau x mu x nu, right? So this thing here, right, is equal to eta mu nu, right? So this just means that this is equal to eta mu nu by comparing the left hand side and the right hand side, or eta is equal to lambda transpose eta lambda. So this lambda transpose is the transpose of lambda matrix, and so basically this is how eta is transformed on Lorentz transformations, and in fact eta is the same, right? In the transformed coordinates, it's always -1, 1, 1, 1 in any frame that you measure it in. So if you take the determinant of it, determinant of lambda squared times determinant of eta. So that means that determinant of lambda square equals 1, or the determinant of lambda, this Lorentz transformation matrix is equal to 1, is equal to. So this matrix has a determinant which is unity, of course, which you can actually verify from this matrix. This simple matrix which corresponds to boost has a determinant which is unity, but this is in general true for any transformation which satisfies the preservation of this interval. Okay, just a sec. Okay, so similarly, we can actually choose, we can actually choose determinant of lambda is equal to 1. We rule out, this rules out reflection. So, we don't include reflection in the transformations that are allowed. But at least the classical physics is the same, even if there is reflection symmetry. But we just consider this for simplicity, and similarly we assume that lambda 0, 0 is greater than or equal to 0. We take positive value of this component. I mean, this is a convention. Okay, good. So this lambda is the matrix which defines the transformation of vectors in under Lorentz transformations or general transformations which preserve, which are consistent with special relativity. What about contravariant components? So this was just x prime mu equals lambda mu nu x mu, right? So this is the transformation of contravariant components of vectors. What about covariant components? What about this? Right, so this is actually represented by lambda tilde nu mu x nu, right? So this, I'm just sort of using another matrix lambda tilde, which gives you transformations for covariant component. And this is the contravariant component. Okay. Right. So how can we relate lambda and lambda tilde? We can actually do that by recognizing that eta is the lowering parameter. So let's see, x mu prime equals eta mu sigma x prime sigma, right? So I said this is always the same in whatever frame you take, the eta, the Minkowski matrix. So this is this, and x nu equals eta nu tau x tau. So using all this, actually you know, there are certain properties that you can prove. You can prove that lambda tilde. I mean, I hope everyone is sort of familiar with manipulations of vectors and tensors using these. Huh?
The two are equal, right? Lambda and lambda tilde.
Yes, lambda. No, they are not equal. I mean, in this particular case, they look equal, but in general, no. I mean, lambda and lambda tilde are actually not equal. Even in this case, there is a minus beta that appears, right? The inverse transform.
Okay.
So, you know, one has to be actually a little careful. Yes. Right. So you know, there. Right. So lambda transpose is the inverse transform, and this tilde thing is the transformation of the covariant components. Let's see the other, you know, there are various such properties. Actually, I mean, I'm not sure how much of this I should really go get into, but you know, you guys should read it from the book. It's given in the book. I mean, I am not going to do a lot of this detail because, you know, there is a course in itself on tensor analysis and all that, and we will just go too far away from the main subject of this course if we get into that. So, I mean, there are certain properties, for example, so lambda sigma nu, right? You know, this is like a mixed tensor. One of them is raised index and the other is lower index. So it's a mixed tensor. Mu sigma is equal to lambda delta function nu mu, right? So, you know, from just these identities, you know, matrix properties, you can actually prove all this. And this is just the delta function in 4D space. So these are some of the properties. So you can actually see, you know, this matrix times this matrix equals identity. So lambda tilde actually is equal to lambda inverse, and that's equal to lambda transpose, because, you know, for these particular properties. Okay, so, you know, the point is you can actually do a lot of sophisticated tensor analysis and come up with very, very useful framework of dealing with physical quantities once you express them as scalars, vectors, and tensors in this four-dimensional space. Okay, but in the end, so for example, in standard physics, right, all our physical laws are expressed in terms of mathematics in form of a scalar or a vector equation, right? And the reason we do that is, if you say, for example, F equals ma, right? This is a vector equation, right? And since you can do like rotations and translations and deflections, this transforms on those transformations to F prime is equal to M A prime. So basically, if you are able to express physical laws in terms of laws relating vectors, scalars, or tensors in this four-dimensional space, then, you know, basically all physical laws must be expressed in terms of tensor equations, right? Because if the theory is if the theory satisfies Lorentz invariance and satisfies the postulates of special relativity, then you should be able to transform them to some other frame, and you should get the same physical law. Okay, so that's why, you know, this concept of vector is very, very deep, in a sense that, you know, once you are able to confirm that something is a vector, And if you write vector A equals vector B, that equality holds in all coordinate systems, right? The same is true for special relativity in this 4D space. So that's why all the physical quantities we should be able to write as 4 vectors, scalars, or tensors, right? Which transform according to these equations. Okay. So let's say, are there some 4 vectors that we are familiar with? So there is right. So there is 4 velocity, right? So we know that x is a x is a vector, right? X mu, for example, is a vector, right? And dx mu is a vector. But this is not a vector, right? Because dt is frame dependent, but not for vector, right? Because dt depends on the frame in which you are looking at. So whereas the numerator does not. But dx mu by d tau is for vector, right? Because d tau, where tau is the proper time is a Lorentz invariant, right? D tau square is equal to c squared d tau square equals c squared dt squared minus dx I dxi, right? So this is just, this is Lorentz invariant. Tau is, so you can actually define dx mu by d tau as a 4 vector, and that's called 4 velocity. So 4 velocity is equal to gamma c and gamma u, where u is the velocity of the particle, right? So let's see. So right, x mu is equal to ct x1 x2 x3. These are the coordinates of a particle, right, in some frame S, and dx by d tau. So this is nothing but c dt by d tau, and we know that dt by d tau is gamma. So this is gamma c. So this is the first component. Similarly, dx I by d tau equals dxi by dt times dt by d tau, which is nothing but gamma times dxi by dt, which is nothing but the actual velocity, right, measured in the frame. So that's why this is a 4 velocity, because this can be written as a ratio of a 4 vector and a Lorentz invariant scalar. So this is the tau is a scalar or a Lorentz invariant. Okay, so this is 4 velocity. Similarly, k, the wave vector, can be generalized into a 4 vector, where the 0th component is omega by c, where omega. So this, this is for velocity of a particle. Okay, so this is 4 wave vector, right, of say an EM wave. So basically what it means is that it transforms according to as a 4 vector. So x0 square minus x1 squared minus x2 squared minus x3 squared should be equal to is independent, right? So what does that mean? So x0 squared is omega squared by c squared minus k squared is equal to omega prime squared by c squared minus k prime squared, and this is equal to 0 for an EM wave, right? So such things where, you know, k dot k, like this is in the four dimensional space. This is, you know, when the scalar, you know, when the magnitude, so this is magnitude, right, in 4 space, like an interval, right? It's 0 quantities, right? So we have these ds squared greater than 0, equal to 0, and less than 0, right? So these quantities which have ds squared greater than 0, they have dt squared, c squared dt squared greater than dx squared. So these are like time, these are called time-like vectors. This is a null vector, or light-like. Right, so this is light-like because, you know, this corresponds to the relation between frequency and wave number of light, and these are space-like. Intervals. Okay, so this is another wave. This is another 4 vector. Similarly, j. This is what? This is velocity. This is wave vector. This is current density. So this is rho times c, and this is j, the charge, the current density. Rho is charge density. And this is current density. Okay. So this is a 4 vector because it satisfies these properties in all reference frames. Okay, so for example, you know, we can actually write, so for example, charge conservation, we know that dou rho by dou t plus del dot j is equal to 0, right? This is the charge conservation, right? So we can write this, right? So this is a scalar equation because, like, you know, I mean, this is a scalar. Rho is a scalar, so dou rho dou t is a scalar. So can we write this equation in terms of the 4 vector equations? In fact, that's what we want, right? If we want our equations to be consistent physically, then we should be able to write such equations in a form which is, you know, this is called a covariant form, right? Covariant form is a form which is written as a vector equation or a tensor equation or a scalar equation. Can we write this in a covariant form? This is not a covariant form because we are not using you know, we are not using 4 vectors here. We are using spatial vectors and time. Covariant form, we should be able to write it in this form in terms of 4 vectors. So let's see, that actually is j mu. So this is the contravariant component of current density, and we want to be, right, we want to write this dou by dou x mu, right? So this is like a divergence. This is like a divergence in 4 space. Okay, and what does it mean? It means you are contracting dou by dou x 0, dou by dou x I, and rho c, and j I, right? So when you're contracting, this acts on this, so you have so x0 is nothing but ct, right? So this is 1 by c dou by dou t c rho plus dou by dou xi. So that's nothing but this equation of charge conservation, but written in a, so this is the covariant form or the vector or the scalar form of the equation, right? Where you're writing some scalar on the left hand side is equal to some other scalar, right? So this is guaranteed to be Lorentz, this is guaranteed to satisfy all the postulates of special relativity because you have written it as in terms of a 4-vector equation. Similarly, all the physics laws we should be able to express in terms of tensor equation. Okay. Let's see. What about any other 4 vectors? Maybe someone can tell some other 4 vectors that they are familiar with.
Energy momentum.
Energy momentum 4 vector. That's correct. So that's energy momentum 4 vector is capital P. This is for a particle it's sort of gamma mc squared, and this is gamma mv, where v or u, where u is the part velocity. So right, so this again satisfies this preservation of p dot p is preserved in the when you're taking the dot product in the 4 space. Okay, what else?
So scalar potential and vector potential.
That's correct. So that's A. This is phi and A. So this is the scalar potential and the vector potential. Right, and these are 4 vectors because they transform according to those lambdas. The same lambda that would transform x to x prime will transform a to a prime. So these transform these transform in the same way as the displacement vector. So that's why they are also vectors. So just a collection of 3 or 4 numbers is not a vector. A vector has to transform according to certain rules, right? So that's the definition of a vector. So that's why it's an important and deep concept. Okay. Right. So let's see. We know this. These are the
phi by c, right? Phi by c and a.
Just a second.
Yes, sir. What I mentioned.
Right. So yeah. So E equals minus grad phi plus 1 by c dou t. Sorry, minus 1 by c. All right. So the dimensionally c. No, this is correct, right? This and this has the same dimensions. So 1 by L. Right. So this is correct actually, right? Or not? Or no. So this is A0, and this is the rest of A1, A2, A3. Phi and A have the same dimensions, right?
Okay.
So yeah. No, this C and so on, there is so much, the point is in this, there are so many conventions, and in the mathematics of tensors, there are so many conventions and places where things can go wrong if you're not very careful. And unfortunately, this is not something that I do routinely. So, I may also make errors, but just please do point out if there's something, but this is correct, I think. Okay.
In Gaussian, in CGS unit, this is correct.
Yes, we are following Gaussian units. We are following CGS units throughout the course. Okay. Okay, so what about some other equations? For example, this wave equation, right? We know this minus 1 by c squared dou by dou t squared. We actually dealt with this briefly. This is satisfying. Both A and phi satisfy this equation, right? right? So I mean, this is actually a 4 vector, obviously, because this is J, the 4 vector J. This is just that. This is also a 4 vector. So this is a vector equation, But can we write it in a covariant form? In terms of not in terms of T and grade, del square, but in terms of like some sort of a divergence or some sort of a operator in the 4-dimensional space. And the answer is, of course, you can. This is nothing but dou by dou x alpha dou by dou x alpha a beta is equal to minus 4 pi by c j beta. Right, so this is nothing but this operator, D'Alembertian operator. Right, you can actually see because x0 equals ct, and the other thing is here in this gradient term, right? When this alpha appears on top, this actually is a when this alpha appears at the top, this is a covariant. This transforms as a covariant component of a vector, whereas this transforms as a contravariant. So this sort of this operator can be thought of as an operator with the lower. I should not call it say let's call it T. This is an operator with the lower index, and this is an operator pi. Let's call it pi 1, pi 2. With an upper index. So these contract to give you something which is a scalar, right? So you have to be extremely careful with this. So this is oops. Just a sec. Okay, right. So we can actually write it in a more convenient form. So this is the wave equation in Lorentz gauge, right? What does it look like? It looks like a beta. So this is a vector, and you do comma alpha here, comma alpha here, right? So what does it mean? This comma alpha here at the bottom means that this is the contravariant derivative. Covariant derivative, because alpha is at the bottom. So this is this. This comma alpha represents this derivative, and the comma alpha at top represents derivative with respect to the contravariant x. So this is a short notation. Again, here alpha is summed over because this is a repeated index. So this is nothing but that equation. So this is equal to minus 4 pi by c j beta. Right. So this is a covariant equation in the 4 space because it expresses a vector on the left hand side and another 4 vector on the right hand side. Okay, and these gradient operators satisfy, they also transform according to Lorentz transformations, right? For example, in other words, dou by dou x alpha prime is equal to, so dou by dou x nu, and there was this so this is like a covariant, so there is a lambda tilde here, okay, and this is like a also nu alpha, right? You can actually show this. So this transforms like this operator transforms like a covariant vector. So that you can actually think of this operator as a covariant vector. Okay, so this is the wave equation. So look, it looks much simpler and elegant in terms of 4 vectors in comparison to this case, which is sort of just the usual derived form. Okay, but this mathematical elegance actually comes because of this whole formalisms of vector and tensors. So this is very, very powerful, and this is what has enabled right, so much progress in relativity and even quantum mechanics, relativistic quantum mechanics. So you should be able to write all the equations in such a covariant form, where you have a 4 vector equation and a 4 vector or a 4 tensor on the left and on the right. So this is Lorentz gauge. So Lorentz gauge condition was, if you recall, was this. So this is a scalar equation, right? The left hand side is a scalar. Can someone tell me the form of this? Can you write this equation in a covariant form?
Del mu mu is 0.
Yes. So this is equal to a mu comma mu is equal to 0. Right. So this, if you have a repeated index at top and bottom, they get contracted. So this will be like a sum over these mu's, and that's what will give you this, right? So this is dou by dou x naught a naught plus dou by dou xi. I mean, the only way to sort of get familiarized with this is to just practice. Okay, and in the end things look extremely elegant, but everyone should try it on their own and be somewhat comfortable with this. Okay, what about E and B? Can we write E and B as in form of a 4 vector? What about electric field and magnetic field? Can we write, say, some general, like we did a generalization of velocity to 4 velocity. Can we generalize E and B to some 4E, 4B? The answer is
You are telling, sir, F mu?
Yes, you have to broaden the dimension, you have to go to a tensor rather than a vector in order to do that. And how do you do that? So, right, we know that, right, so E and B, right, you recall E was equal to minus 1 by C, now A, now T, minus grad phi, and B was equal to del cross A. So you can see that E and B are sort of gradient operators in the 4 space, applied to A, right? So you can actually write in terms of things like, right, these type of operators, dou by dou x nu A mu. Okay, so and E and B are six components, right? E and B have 6 components, right? And they are sort of combined in a single entity, right? Because we know that electric field in one frame of reference can become magnetic field in the other, and vice versa. So these get mixed just like space and time get mixed. But these are 6 components, so we cannot possibly put them together in a 4 vector. What you have is this antisymmetric tensor called F mu nu. Right? This is the antisymmetric F mu nu tensor, which is defined as A, and here I'm using the covariant components of f. This is a nu comma mu minus a mu comma nu. Right, so this is what we define this f, this antisymmetric tensor as, right? This is antisymmetric because f nu mu is just the negative of f mu nu. So it turns out that you can write, these equations for E and B, right? So these equations can be written in a more in a tensor form, in a covariant form, if we introduce, if we recognize that f mu nu, right? This is, yeah. So let me just write down f mu nu is equal to just a second. I don't want to make a mistake. Right, so this is equal to, in fact, I find that the book has a typo. So this is 0 ex ey ez and minus ex. I mean, this is antisymmetric, minus ey minus ez. Of course, there are zeros here on the main diagonal. Then this is minus bz, by minus bx, and by antisymmetry this is bz, this is bx, this is minus by. Okay, so you can actually verify by by plugging this in and using this definition, using this and this, you can verify that your E and B satisfy these equations. Okay, and this is the famous antisymmetric F tensor, and I think this is equation 4.59 in the book, and I think that there is a typo in the sense that I find that these are all negative. In the book the signs are all reversed, but I think this is correct. I also checked it in Jackson, so just please check. Maybe I have missed something, but please check that equation 4.59 in the book should have negative values of what they have in the components. Now, what about the Maxwell equations? Maxwell's equations are, right, so this del dot E equals 4 pi rho. The rho is charge density, and del cross B minus 1 by C dou E dou T is equal to 4 pi by C times J. Right, so these are homogeneous Maxwell's equation where there are source terms on the right hand side. Can we write this as in terms of can we write this in covariant form? And it turns out that indeed you can. So this is nothing but f mu nu comma nu. Right, so this is nothing but tau by dou x nu f mu nu. You have to be very careful about the where the index goes, whether it goes on top or at the bottom, subscript or superscript. This is equal to 4 pi by C J mu. Right, so this is written in terms of the covariant components. I mean, if you just multiply it by eta, you get, you can raise or lower the indices. Okay, so you should check whether this, this is a vector equation, right? So you're contracting mu, and you have an equation which is satisfied for mu equals 0, 1, 2, 3. So these are actually 3 equations, right? And sorry, 4 equations, right? Because for mu equals 0, 1, 2, 3. So so mu equal to 0 must be this one, right? This is the equation for mu equal to 0, and these are the mu equal to 1, 2, 3 equations. Let's see if mu equal to 0 is that. So that's I actually don't want to do this. It takes a lot of time to do these things, but you should definitely verify. And I spent a lot of time actually trying to convince myself that there is a typo. The book is actually very good. If you guys have read it, there are not a lot of sloppy mistakes. Okay. So what about charge conservation, right? So the charge conservation equation, of course, we can write as J mu comma mu is equal to 0. This is just the charge conservation equation. We already wrote that earlier, but we know that this is 4. We can actually just put the 4 pi by c here, so that this equation, the right hand side is just this. You just contract it with mu. So what do we have? We have this is equal to f mu nu comma mu nu, right? So this is the equation. All you are doing is contracting with mu. So here you just put a mu on top. Here it's the same as this. So this is equal to 0. So this is charge conservation expressed in terms of the fields E and B or F. Okay. So let's see, what else do we need? What about the other equations? Del dot B. These are the homogeneous equations, and del cross E, which don't have a source term on the right hand side. What about these equations? Can we write this as in a covariant form? And the answer for this is indeed you can. So this is f mu nu sigma plus f sigma mu nu plus f nu sigma comma mu is equal to 0. So this is just like a cyclic permutation of indices. So and this actually is valid for mu equal to mu. So these are actually how many equations? Can someone tell me? If you write these out, how many equations do they correspond to? This is a third order tensor equation. Right, so
there is antisymmetry. So there will be,
yes, that's correct. So they are not all independent because F is antisymmetric and there are other properties. So otherwise it's 4 times 4 times 4. These are 64 equations, but they are not all independent. They are just these equations, right? If you reduce them to the independent one, they are these 4 equations. Okay. Good. Okay, so this is this is just a little bit of a flavor actually of this mathematics of tensors and special relativity, right? But as I said, we are really not doing special mathematics of special relativity. We are applying special relativity to get stuff related to radiation that we want, but in the process we also do a little bit of that. a little bit of this tensor analysis, but not at all in any rigor. So a lot of these results that I've stated may sound you like out of blue air, and that's true actually, because I've not really motivated them enough. But anyway, so if f, sorry, let's see. So f, f is this antisymmetric tensor that we introduced. In fact, we can actually write f mu nu, right? It's an antisymmetric tensor, and since it's a tensor, second order tensor, we can actually write how f transforms, right? This is a covariant tensor, so it must transform with lambda tilde, right? So let me actually, so tilde is for covariant transformations. So f alpha beta. So in the unprimed frame, and then we have to just put the indices mu alpha and beta and nu. Right. So this being a Lorentz, f being a tensor must transform like this. And if we plug in the form of f in terms of, f is basically, in terms of E and B, it's sort of related to it. If we plug that in, we can actually get Lorentz transformations. So we can get Lorentz transformations for fields E and B. Okay. Right, it's sort of somewhat tedious, but the answer that you get can be expressed in simple form. So this is actually the Lorentz transforms of the fields. So let me actually write it out. So suppose you have a velocity v, right? So you want to go from, you recall, don't forget this. You are in this frame S, and you have this frame S prime, which is moving relative to it with the speed v, right? So what we are actually trying to do is, you have E and B measured here. You want to see how these E and B, what are the values of these E and B in this frame, and the value is actually given by these transformations. But if we express it in terms of more usual, in the more usual way, what do we get? So we get E parallel prime is equal to E parallel, and B parallel prime equals B parallel. What does it mean? So parallel is with respect to V. So B parallel or E parallel is equal to B dot V hat, right? So so basically these are the field components along the direction of the boost, Lorentz boost. So if you do all this algebra, you will see that the parallel component of the fields E and B do not change on doing this boost. What about the perpendicular component? E perp prime actually is equal to gamma E perp plus beta cross B perp. Beta cross B perp or beta cross B, because beta cross B parallel is 0. So let me actually just ignore this B perp, just write it as B. Right. So this is how the perpendicular component of electric field to the direction of boost transforms, and this is how the and these are actually vectors, because there are two spatial directions perpendicular to the velocity. This is equal to gamma B perp minus beta cross E. So these are this is how the fields transform. So this is not like a general, this is not Lorentz transformations, right? For this is not the Lorentz boost formula, right? This is actually transformations. Maybe I should transformation of fields, but this is not of this form that the parallel component. For example, x prime equals gamma x minus vt, and t prime equals gamma t minus v x by c squared. Right? This is not of that form. Okay, so this is for B. What about right? So what it means is that E and B are mixed. The E and B are mixed, and they depend on frame dependent, right? Just like space coordinates x and t get intermixed because of x and t get intermixed for particles traveling close to the speed of light. Similarly, E and B get intermixed for fast moving particles. So that's why you should really think of electromagnetic fields rather than electric fields or magnetic fields in general. Okay, so there is this mixing of E and B similar to mixing of space and time. Space and time do not have independent existence. They become space-time in such a way that this interval is conserved. In the same way, E and B, if you have E and B in some frame, it can actually be totally transformed into electric field if provided that this beta satisfies this, right? So this is very, very different from the usual concepts that we have. What about any other Lorentz invariants in terms of E and B, right? Can we form any Lorentz invariants? So, how do we form Lorentz invariants? Lorentz invariants are basically scalars like ds square, which is equal to c square d tau square. Can we form them out of these antisymmetric tensors f mu nus? For example, this f mu nu, f mu nu, you're basically contracting both the indices. So this has to be a scalar. It would transform like a scalar. And what does it, if you plug in the form of f in terms of E and B, this corresponds to 2 times b squared minus e squared. In fact, you can actually you can actually use this and show that 2 times e square minus b square is equal to 2 times b prime squared minus e prime squared. So this is a Lorentz invariant. It's a scalar basically. So 4 scalar. It basically, its value remains the same in whatever frame you look like, in whatever frame you choose to look at it. Similarly, determinant of f, right? Determinant of a matrix is a number. So this again is a Lorentz invariant because it's a number. And what does it correspond to in terms of E and B? It's E dot B. So E dot B is equal to E prime dot B prime. You can actually show it using these forms. This is another Lorentz invariant. Okay. And there is a physical way of looking at some of these transformations. Let's say, this was mathematics. Mathematics is beautiful. Once the formalism is established, you can almost mechanically work through the tensor algebra. But that requires a lot of work in order to convert all these physical laws into pure seamless mathematics. Okay, so let's see, is there a way in which we can actually see these transformations of electric fields and magnetic fields that are written out here? Let's actually consider some simple examples. Let's consider case 1. Okay, so you have, then let's consider a charge capacitor. You have these two plates, positively and negatively charged. Okay, and so this is, this is in some frame, and now, so this is frame S. Okay, now you consider another frame, S prime. So in frame S, these capacitor plates are at rest. In S prime, you are moving with a velocity v, right? So what happens in this case? In this S prime frame, what happens? So this length, let's say this is d in the S frame, right? So d becomes d prime, d prime in the prime frame is equal to, there is Lorentz contraction in this direction, right? So d prime, the length of this gap between these two plates becomes d divided by gamma, right? What about the charge density on these plates? Does it change or not? Does sigma, the charge, see the amount of charge will not change, because charge is a scalar, it's a Lorentz invariant. Total charge is a Lorentz invariant. What about sigma? Does it change in this moving frame? Sigma prime is equal to, see, the contraction is happening in this direction, not in this direction, right? So sigma prime is actually equal to sigma, because stuff is thinning in the direction perpendicular, in this direction. So the charge per unit area remains the same, because the perpendicular area does not change. It's only the longitudinal length which changes. Do you get this?
Yes, sir.
Yes, sir.
Okay, good. So what about, so electric field is of course in this direction. Let's call it x direction. So Ex, right, in the lab frame is what? 4 pi sigma x hat, right? This is in the lab frame. What about in the primed frame? What about in this frame, in the primed frame? Right, so we know charges in the primed frame, right? And the electric field does not depend on the distance between the capacitor, right? So it's just sigma by epsilon naught, right? It doesn't depend on how much the gap is. It only depends on sigma. So Ex prime again is 4 pi sigma x hat and is equal to Ex. So what does it mean? It's consistent with E parallel prime is equal to E parallel. So electric field in the direction along the boost, right? The component of electric field along the direction of the boost does not change, right? This also we get from the consideration of charges. Is this clear? So this is just a little physical way of, reconciling the equations that I wrote. For example, this equation, this is this one, right? So I just written that mathematically. Here you can actually see physically in terms of how the charge densities themselves are changing. But in the end, you have to get this in order for it to be consistent. Get it? Let's consider one more example. For example, in this case, let's consider this geometry. So you have this and this. Again, you have charges like this, and the same frames. So this is in the rest frame now. What are the electric? This is the electric field direction. E. Okay. What about sigma? So sigma is in the lab frame. What about sigma prime now? In this case, what will be the value of sigma prime? The charge density?
Sigma by gamma.
Right. Sigma prime is sigma by gamma. Why is that? Because the contraction happens in this direction. So one of the length of the capacitor plate will reduce. If the length reduces, area reduces, and if charge is the same and area is less, the charge density becomes this. Okay, so this is just a consequence of length contraction. So what about E prime is equal to, now in this case E prime will actually be sigma prime, 4 pi sigma prime. So this is again x direction and this is y direction. Okay, and z is out of the board, out of the plane. So E prime equals gamma E in this case. In fact, it's E perp, right? This E is E perp because velocity, this electric field is perpendicular to the direction of the boost. We are again considering the same boost in this situation, just orientation of the capacitor is different. Okay, what about magnetic fields? What about, so here, for example, let's go back here. What about B? What about B prime? So in the lab frame, B is actually 0. What about B prime? Right. So in this case, the charges just get closer. There is no, there is just contraction of charges. There is no motion of charges. So B prime is actually 0. Okay. So B prime is 0. E parallel prime is E parallel, and B in the lab frame is 0. What about B prime here? Right now, in this case, when if you go to the frame S prime, these plates are actually moving in that direction, right, with respect to the observer. So there is a current.
So
Yes.
sigma prime is sigma gamma times sigma, right? Because the charge density will increase since the area is decreasing.
Sorry, yes, you're right. Yeah, and also E is proportional to sigma, so this is not right. So area decreases, so sigma increases. Sorry about that. Okay. What about the current density? So these, in this frame, you have these positive charges moving with negative velocity. So your K prime, right, in this frame, measured in this frame, is actually equal to, so this is charge per unit length. Sorry, current per unit length, per unit length. So basically, if you have charge density and if you multiply it by the thickness, you get this. So this is equal to, and we are sort of considering this bottom plate. So what is the charge? What is the current surface density at the bottom corresponding to the bottom plate? This is just minus sigma prime times V. And these are positive charges moving in the negative direction, right? Because if for the observer, for the observer which is moving in the positive x direction, the bottom plate is moving in the minus y direction, minus x direction, and charge density is nothing but current density is nothing but charge density times the velocity, and that is nothing but minus gamma sigma V x hat. Okay, so this is K prime. So if you have currents in this direction in the primed frame, you will also have magnetic fields, right? Currents cause, so B dot dl. I mean, in fact, we are just writing it in prime frame is equal to 4 pi by C I enclosed. And this is again in the prime frame. Everything is done. These measurements are done in prime frame. So what do you get for that? So so B, right? So just here is equal to, right now you can actually construct a Amperian loop like this, right, in the prime frame, and this is the current density. So B times so this is perpendicular to the direction of motion. So B times, so let me just forget about the magnitude. So I know that, if since the current is going in this direction, minus x direction, I know that there will be magnetic field in the z direction, right? So so B, let me actually just write down. So B prime equals, so B, times the area, right? The area is, some area. Let's consider this. So this is actually an Ampere's loop in the YZ plane. So B times this area equals 4 pi by C times I. I is what? Minus gamma sigma V, and so this is per unit. This
It's a
is
length, right? It's line integral.
Yes, it's a line integral. So right, so it's basically delta y. Right. Right. So this right. So this is Ly, and this area is nothing but Ly times Lz. So just so B prime is actually equal to minus 4 pi by C K prime in the Z direction. Let's see if at least the direction matches. Okay, so B prime, because the current is in the minus x direction, and so current is, if I make a Amperian loop, B is into the board, which is the minus Z direction. So this is B, and this is K prime. Where is my length factor missing? Oh yeah. So this is This is also Ly. This is not B dot ds. I'm sorry. So yeah, this is B dot dl. So right, this is Ly. So you're basically you're basically considering a very thin Amperian loop in the y direction. Extent in the y direction is thin, so you are basically getting this. So right, and this is nothing but minus gamma beta cross E, which is E perp. Actually, E perp is equal to E. So basically what you see is in the lab frame B was 0. Right, in the lab frame B was 0 because there were no currents, charges were stationary. But in this frame, in which the boost is perpendicular to the electric field, there is a magnetic field which emerges. Okay, and this actually, we already saw this mathematically here in these transformation laws. So in special relativity, for example, it's always good to go back to these physically intuitive situations rather than just deal with vectors and tensors, because this sort of gives you a little more intuition as to what is going on physically. But they are, they have to be consistent with each other. If you find something which is not consistent, means that something is not right. And this, of course, is in the perpendicular direction to beta. So beta parallel prime. What is beta parallel prime? What is the electric field along the direction of boost? In this direction, what is the magnetic field? Because the currents are in the same direction, as x, you cannot have b in the x direction. So b parallel prime is equal to 0. So this is actually consistent with those transformation laws that we wrote down. And you can similarly, like these capacitor plates, you can actually consider solenoids and look at some other special cases. But of course, these equations are mathematically precise and they get the right answer in all situations. Of course, that has to be true. Okay, so in the next class we will start looking at implications of relativity on radiation, right? Basically, we'll be considering Larmor power in the instantaneous rest frame of a charge, and then transform it to the lab frame, and all this background that we developed in relativity will be useful there. So that really is the purpose of doing all this. Yeah, that's why we really don't go in great detail with the tensor manipulations and so on. Okay, any question? Oops. Any question? No? Okay, then I will stop recording. And so this